So the last part of this lecture is about inverse functions. So it turns out that once we have a given function, we can always find a new function which basically undoes what the original function did, and that's going to be the inverse function. So the opposite of what you do with a function is what you do with the inverse function. So let's have a look at what that means with an example. So the example here is about demand. So you know a bit about demand from your microeconomics course. You know that the demand for a product will typically depend on the price that you ask. And so it might, for instance, take this form of this demand function that you see here on the slide. D equals the demand equals 100 minus a half times the price. So the higher the price, the lower the demand, which is what you expect of a demand function. So D, the demand, is a function of price, right? So essentially it's function f of p, f of the price. And this function is 100 minus a half p. So it's a nice and linear function. So now the question here is, suppose that we know what the demand is. So you observe demand in the market, say, and or you know how much you can produce, and you want to set the price in the market in such a way to fulfill demand. The question, of course, is, how high should I set the price in order to make demand equals what I want? And what you need to do for that is to figure out what's the inverse function to this demand. So how would we study that? Well, let's have a look here. If we know that D equals 100 minus a half times the price, what we would like to do is we want to figure out what the price is. So let's try to isolate price rather than P, rather than D. So can we bring P to the left-hand side and have some expression in terms of demand, D, on the right-hand side? So if D equals 100 minus a half P, well, can we sort of rewrite this? Well, not so difficult. So bring 100 to the left-hand side by subtracting it from both sides and multiply by minus 2, and then indeed already P is there on its own. So P equals 200 minus 2D once we get rid of the brackets. Or in other words, the price function is given as a function of demand, and here I call this function G of D, and this function is 200 minus 2D. So the original function f of p, which was equal to demand, tells us how large demand is if we know the price. The inverse function does the inverse. So it tells us if we know the demand, what should the price be? So G is the inverse function of f. So before we go into this in a little more generality, there's one thing that I need to say some things about, and that's some characteristics of a function, in particular when is a function so-called one-to-one function. And the idea is a function f, say, which goes from some domain, let's call it A, right? That's what you can put into f, that's the A over here. And B, which will be the range. A function f is a one-to-one on this domain A. If for each possible value in the range, or the y value if you wish, there's just exactly one value in the domain in A, such that indeed this function maps this input from the A domain into exactly this one value of y. So the function on the left hand side is indeed, for this is indeed true. If I point out, if I take one number on the y-axis inside the range, say this one, then indeed there's just one single x which maps through this function from A to B. On the right hand side, this function is not one-to-one, because suppose I take this value y1, which is indeed in the range of this particular function g. This y1 can be reached from two different starting values, two different x values that you plug in this function g, because both x1, if you apply the function g to it, gives me this height y1, but also x2 ends up at the same y1. So you can imagine that there's going to be a problem if I want to introduce an inverse function for this function g over here, because what should this function do? Well, it should map the output, the y1, to the input. Well, here there's actually two possible inputs which might have gotten the same y1, so that's going to be sort of ruin our expectations that we would like to have a single function that maps from y to x, the inverse function. So one way, which is actually satisfied in this example, for a function to be one-to-one is when it's strictly increasing, so just going up, or strictly decreasing. But there might be other examples if the function is actually not contiguous. So with that in mind, we can actually define what the inverse function is. So if f is our starting function, a function with some domain A and some range with a set of outputs B, then this f will have such an inverse function, let's call it g, which will have the domain B, so the original range will become the domain of g, and the original domain of f, A, will become the range of g. So this function, this inverse function g, will exist only if f is indeed such a one-to-one function. So within this course, of course, if I'm going to ask you to determine the inverse function of some given function, you can assume that this function is going to be a one-to-one function, otherwise I would be fooling you, right? And I'll try not to do that, not too often at least. So the question now is, how do we do this? How do we determine what this inverse function is in general? So we know how to work with this demand and supply and price function, but how do we do this in more generality? Now here's a whole list basically. Suppose we want to determine the inverse of f, it says, and if g is, well, I used to call this g, this inverse of f, the most convenient or the most usual choice actually is this f with a -1 super index appended to this instead of using g. So that's sort of an accepted notation within mathematics. So f with -1 as superscript, that typically means the inverse function to this function. Now here's a whole list of steps of what we should take in order to find what the inverse function is. But rather than going through these steps, let's just go through an example and see how these steps work. So the example here is find the inverse function of this function f, which in this particular case is 4x minus 3. So particularly this 4x minus 3, of course, is a linear function. So this particular function describes a straight line, right? It's a linear function. And here's actually the graph of this function. And we're asked, how are we going to produce now, to compute the inverse function to this linear function now? So let me go through those steps on paper. So the question is, we have this linear function, f of x equals 4x minus 3. And first thing, the first step essentially here is, well, let's just make sure that we agree on what the domain, in particular the natural domain, is of this function. Well, in this particular example, there's actually no restriction that we could possibly have necessarily have on f. So actually the natural domain of this function is any number, or in other words, all the real numbers, right? The whole number line, if you wish. So that's the first part, the first step that we should take. The domain of this function is all the real numbers, any number between minus and plus infinity, if you wish. So the second step is let's write this function now in this format that we sort of are accustomed to, with a y equals the output of the function, so 4x minus 3. And now what we want to do again as the next step is we want to isolate this y. So can we rewrite, isolate the x. So can we rewrite this expression in such a way that the x is going to appear on the left hand side, and on the right hand side we will have this expression in terms of y. So let's do that. That's just some manipulation of this expression. So what we'll do is we'll add 3 to both sides, I guess. So y plus 3 equals 4x, or in other words, x equals, if I divide by 4, a quarter y plus 3/4. So now I've rewritten this expression with x on the left hand side and an expression in terms of y on the right hand side. Now we are there essentially. The only thing that remains to be done is say, well, this must be the function that's going to be the inverse function of f, and typically we would like to write this inverse function not in terms with an input y, but we'll call it an input f. So I'm going to switch around the meaning of what we term y and what we term f, and basically what I'm going to say is the inverse function of f. Remember the notation f with this superscript -1 means the inverse function to f. If I put in some x, then what I need to get as an output is this expression that we have here, where now I replace the y with an x, because we like to write functions with x as an input rather than y. So so this is almost it. So this is what the inverse function is. We also typically would also like to know, well, what's actually the domain of this inverse function, and of course again here the natural domain of this inverse function is again going to be all the real numbers. So any number goes. So this funny arm, it's just any real number. So this gives us the inverse function to this function. So let's get back to the slide, which precisely has these same steps. So this inverse function here is called g, so I'd like to call it f with a -1 superscript. If you look at the graph of this, so this was the original function, right? This steep function f, 4x - 3. If you look at the graph of gx, the inverse function, you see, of course, it's this 1/4 x plus 3/4, because that was what we found for the form of the inverse function. But if you look at the graph, you also see that something peculiar or special. It's exactly the mirror image of the graph of f if we use as a mirror this dashed diagonal line, and that's actually a general feature. If you look at a function and draw its graph, and then compute the inverse function and draw the graph of that inverse function, then that graph actually looks precisely as turns out to be exactly the mirror image of the original function, with as a mirror this diagonal line. Let me give one final example, because that's going to be important, and then we can actually we're at the end of this lecture. So you remember from last time we had from the earlier part of this lecture, earlier video, we looked at this certain special function. One of these was the exponential function, which looks like this, right? So e to the power x. This is x. This is y. And we also looked at a different function after that, which was the logarithmic function. The logarithmic function looked more or less like this. And if you now look closely, and you will not be surprised given the way in which we define the logarithmic function, the logarithmic function is actually the inverse function. So the logarithmic function is actually the inverse function to the exponential function. So if you look at the graph, also it's I would have drawn this precisely. It would be exactly the mirror image of the graph to the exponential function would be exactly the logarithmic function. So with that, let's end this lecture, and we'll see each other hopefully again next week.